In this video, we will discuss how to determine the pH of an acidic solution and some of the assumptions that are used in making those calculations. The way that we determine the hydronium ion concentration and the hydroxide ion concentration for strong acids or strong bases is fairly easy. Essentially, there are two sources of hydronium ions in an aqueous solution when we're adding in a strong acid. The acid provides some and water provides some through autoionization. Similarly, for a base, there are two sources of hydroxide ion concentrations in an aqueous solution when we're adding a strong base, the base itself and water. For a strong acid or base, the contribution of the water to the total amount of hydronium ions or hydroxide ions, depending on if we're talking about an acid or a base, is generally negligible. The hydronium ion concentration for an acid shifts the Kw equilibrium so far from where it would normally be in a neutral solution that the H3O plus from water is too small to be significant. Essentially, it's lost in our significant figures. The exception to this is if we're working with a strong acid that is very dilute. For very dilute strong acids, where the concentration of the acid in the aqueous solution is less than about 1 × 10⁻⁴, the amount of hydronium ions coming from water at that point might start mattering. The way that we're going to find the pH of a strong acid or strong base solution depends on what we're dealing with. For a monoprotic strong acid, so that is a strong acid that provides only one proton into solution or gives you one hydronium ion, the concentration of the hydronium ions are essentially equal to the concentration of the acid that you added. For polyprotic acids, those are ones where there are more than one acidic proton that can be donated. Most of the time, generally that is, the additional hydronium ions can be ignored. However, this is not always the case. For H2SO4, the second ionization cannot be ignored. The second proton to come off has a sufficiently high Ka that it provides enough protons into the aqueous solution that those second set of protons can contribute to changes in the pH. However, if we're dealing with a monoprotic acid like hydrochloric acid, if we have a 0.1 molar HCl solution, it has a hydronium ion concentration that is equal to the concentration of the acid that we stated. So the concentration of the hydronium ions are going to be 0.1 molar. If we take the negative log of 0.1, that gives us a pH of 1. For a strong base, the hydroxide ion concentration is generally equal to the number of hydroxide ions that are present in the ionic base. So like calcium hydroxide, CaOH2, if it dissolves into solution, there is a question of the KSP, but if it dissolves in solution, it's going to give up 2 hydroxide ions. So the concentration of the hydroxide ions in solution would be twice the concentration that is reported for the ionic base. For molecular bases with multiple lone pairs that are available to accept acidic protons, generally only the first pair accepts an acidic proton. The others are generally held in reserve for increasingly acidic solutions. An exception to this would be for highly negatively charged species like the PO43-. So if we have calcium hydroxide, for example, a 0.01 molar calcium hydroxide solution, assuming that all the calcium dissolves, would have a hydroxide ion concentration that is twice what was reported for the calcium hydroxide. The reason for this is that when the calcium hydroxide dissolves, it's going to give up 2 hydroxide ions, so that the OH- concentration would be 0.02 molar. If we take the negative log of that, that would give a POH of about 1.7, which correlates to a pH of 12.30. If you're in doubt about whether or not something will fully disassociate, you should check the Ka, Kb, or the Ksp values, depending on what you're dealing with. So let's try an example calculation for how we would determine the pH, pOH, H plus, and OH minus concentration for a strong acid. In this case, we're going to be working with a 0.025 molar hydrochloric acid solution. Because HCl is a strong acid, we know that the concentration of the H plus ions are going to be equal to the concentration of the acid that is listed. So that would be 0.025 molar. The pH is equal to the negative log of that value, which would be equal to 1.60206. In terms of significant figures, the number of significant figures in the value that you're taking the negative log of tells you how many digits after your decimal place your significant figures end. So because we have two significant figures here, that means we get 2 decimal places in our value. So the pH that we would list as our answer would be 1.60. Now, because we have the pH, we can find the pOH, because pH plus pOH is equal to our pKw, which is equal to 14. So to find the pOH, our pOH would be equal to our pKw, which is 14, minus our pH, which is 1.60206, with the significant figure ending right there. So this would be equal to 12.3979, with the significant figure being between the 9 and the 7. So the pOH that we would report would be 12.40. Now the OH concentration we can find, our OH minus concentration, is equal to, we can take our pOH, 10 raised to the negative of the pOH will give us our OH minus concentration. So this would be equal to 10 to the negative 12.40. That will give us 4.0 times 10 to the negative 13th. Now, we could also find this, the OH minus concentration, by using our OH minus concentration times our H plus concentration is equal to our Kw, which is equal to 10 to the minus 14. So our OH minus concentration would be equal to our Kw, 10 to the minus 14, divided by our H plus. So that would be 0.025. So that also gives us 4.0 times 10 to the minus 13. Our answers for our H plus concentration are 0.025 molar for our pH, is 1.60 for our pOH, it's 12.40, and for our OH concentration, it's 4 times 10 to the negative 13. Now, the way that we find the pH for a weak acid, unfortunately, is a little bit more complicated. For a weak acid, there are also 2 sources of hydronium ion concentrations in an aqueous solution. Again, the acid and the water. Unfortunately, this time, the hydronium ion concentration is complicated by the fact that the acid does not disassociate completely. So what we need to do is figure out, for the acid, how much of it has been converted into the conjugate base, i.e. how many of those acidic protons have been donated. Because this is an equilibrium system, the way that we're going to figure that out is by solving it as though it's an equilibrium problem using an ice table. So let's work through an example of how you would find the pH, pOH, Kb, pKa, and pKb of a weak acid like HF, which has a Ka value of 3.5 times 10 to the negative 4th. So let's say we're dealing with a 0.250 molar hydrofluoric acid solution. Now, because this is a weak acid, in order to figure all this out, we will need to make an ice table, right? Because we're going to treat this as an equilibrium. So first thing we need to do is write out the equation, the chemical equation for the reaction. So this would be HF breaks apart into H plus F minus. And we have our initial, we have our change, we have our equilibrium. This starts out as 0.250. We're going to assume that the concentration of hydronium ions coming from water is negligible, so we'll set that to 0. For the fluoride, there's no mention of it in the problem, and so we'll also treat that as 0. So because there are no products, the reaction cannot go back to the left, so it must go to the right. So this one, the reactants will go down, our products will go up by X each. So at equilibrium, we'll have 0.250 minus X, H plus will be X, and F minus will be X. Because we're talking about equilibrium, our equilibrium constant, in this case for an acid dissociating, is going to be the concentration of our products divided by the concentration of our reactants raised to their respective powers, leaving out any pure solids or pure liquids. So that would be H plus times F minus over the concentration of HF. So that's going to be equal, plug in our values from our E row to X times X divided by 0.250 minus X. Now, this is X squared on top. We're going to make the assumption that the X here is insignificant compared to the number, just like we were doing with equilibriums before. So we're going to assume that X is much less than 0.250. Our cutoff again is 5%. So what that does for us is our Ka value would then be X squared over 0.250. We can rearrange to solve for X, moving the 0.250 to the other side. So 0.250 times our Ka value is equal to X squared. Then we take the square root of both sides, giving us X, which if we're looking at our ice table is equal to the concentration of our hydronium ions, our H plus ions. This is equal to the square root of 0.250 times our Ka, which is 3.5 times 10 to the negative 4. All that is being square rooted. Plug that into your calculator, you'll find that it's 0.00934. In terms of significant figures, our Ka value only has 2, and so our answer will only have 2 significant figures. This is molar. Now, before we proceed, we should check that our assumption was valid, and so we'll do that by taking our X, 0.009354, divided by the number that we assumed that it was insignificant compared to, and multiply it by 100%, and we find that it is equal to about 3.7%. So it's within our cutoff, it's within the 5%, and so we're going to say that it's a valid assumption. So this value here is the concentration of our H plus ions. from that, we can find our pH. So pH is equal to the negative of the log of our H plus concentrations. So that would be the negative log of the 0.009354. If you take the negative log of that, you will find that the answer is 2.02900. So because here we had two significant figures, when we're doing the negative log, because we have two significant figures here, that means our number will be cut off after two decimal places. Right? So our answer for our pH would be equal to 2.03. Now that we have the pH, we can figure out what the pOH is, because pOH plus pH is equal to our pKW, which is 14. And so our pOH would be equal to our pKW, 14, minus our pH, which is we'll use the 2.02900. So 2.02900, sig fig right there. That will give us 11.9709998. There's actually a 2 back here. In terms of significant figures, the 14 actually would have more. It would be 14.000. Minus this has 2 decimal places, and so our answer would be accurate to there. So our pOH would be 11.97. Okay, because we have our pOH, we can find our OH. The concentration of OH minus is equal to 10 to the negative of the pOH. So that would be 10 to the negative 11.9709998, which is 1.06906 times 10 to the negative 12. Our value here has 2 decimal places, so when we take 10 raised to that value, or 10 raised to the negative of that value, we will have 2 significant figures, so it gets cut off there. And so our OH minus concentration will be 1.1 times 10 to the negative 12th. Okay, so we now have our H plus, we have our pH, we have our pOH, and we have our OH. Okay, now we're going to find our pKa, pKb, and Kb. So our pKa is equal to, well, it's pKa, so it's the negative log of our Ka, which would be the negative of our Ka value up here. So if we take the negative log of 3.5 times 10 to the negative 4, that is 3.4559. Because this value, our Ka has 2 significant figures, our value is going to be accurate to 2 decimal places. So that means that our pKa would be 3.46. Our pKb, so our pKb plus our pKa is equal to our pKw, which is 14. So our pKb would be equal to our pKw, 14, minus our pKa, so that would be 3.46, giving us a value of 10.029 0.54. The last value we need is the Kb. Kb is equal to 10 to the negative pKb. So if we take 10 to the negative 10.05, that gives us 2.857 times 10 to the negative 11. Because this is accurate to 2 decimal places, our value will be good to 2 significant figures. So that means it is 2.9 times 10 to the negative 11. So that gets us our pKa, our pKb, and our Kb. Right? So those are all the values that we'll be after. You can see that calculating the values for a weak acid is a good bit more difficult than calculating for a strong acid, but as long as you approach it slowly and methodically, it is quite doable.